Hello everyone. In this particular class, we are going to look into the topic of unsteady state material balance for the case of CSTR, continuously stirred tank reactor. Let's look into that in detail. Here is the case. You may pause the video and note down the numerical. This is a generic derivation type of problem. Once you have copied down, once you have read the problem, you can go ahead with the video. Okay, now I assume that you would have read it. Anyways, I'll explain it in detail. So this is the block diagram that we can draw based on the concept or the numerical that is explained or given. Let me give you the idea of CSTR. CSTR means a continuous stirred tank reactor. The meaning is you have a tank in which a stirrer is present. It will be continuously mixing. The feed stream enters continuously with a particular flow rate and the product exits. So it's a continuous reactor in which the reaction is going on. So since there is a mixing, we assume that there is a complete mixing. For the reason why we need a complete mixing is the concentration of any chemical inside this tank should remain constant anywhere. With respect to space, the concentration should not vary. It should remain the same. One more thing you need to note is that when the exit takes place, when the product stream goes out, the concentration of a given chemical in the product stream remains the same as it is inside the container. So the concentration in the container and the exit stream concentration of any chemical remains the same. That's the usual what you say strategy that we use considering uniform mixing. If the mixing is not proper, then there will be difference. So our assumption will state that there is a uniform mixing. So let me explain you the problem. We have a continuous stirred tank reactor. The volume of the liquid inside the tank, please note, volume of the tank and liquid in the tanks are different. Usually the tank is not completely filled, it is partially filled, possibly around 75% approximately. So let me take the volume of the liquid in the tank as V meter cube or V liter, whatever it's a unit of that. The feed enters with a volumetric flow rate. So the volumetric flow rate of the feed, we note it, that is Fi, and it leaves with the particular volumetric flow rate as F0. The concentration of reactant, a given reactant A in the feed, it comes along with the feed as a part of the feed because that A is dissolved in that liquid which is coming in. There's the feed there. So let me take that particular concentration of A as CAI, representing inlet concentration of A. Concentration of the same chemical A in the exit stream, let me denote it as Ca0. Usually we write it as Ca only, provided the concentration of reactant in the liquid mixture in the tank and the exit remain the same. The density of the feed stream is rho I and the density of the product stream is rho naught. Let us define this input and output density of the streams is rho I and rho naught. The difference between the density and its concentration is that the density here refers to the concentration, that is in kg per meter cube, of the whole stream, the complete stream. When I say the stream, it includes, along with the, if there is any other chemical coming in, it includes that. It includes the solvent also. Whereas when I say Ca, I mean the concentration of that particular chemical A in that incoming stream or exit stream. So we are referring to only the one chemical A. Whereas when I say stream, that is rho I, when I am considering, it includes all the chemical including the solvent as well as A put together. So there is a small difference between two things, C and rho. So we'll assume the tank is well mixed. The concentration of A in the tank, inside the tank, is Ca. Since it is well mixed, you can refer that Ca and Ca0 are same. Exit concentration and the concentration of A in the tank is same. That's our assumption. Density of liquid in the tank is rho. So it enters as rho I. Inside the tank it is rho and exit is rho naught. So what we can do is we can make it as a constant density system. We can assume it later and we'll verify that. In the reactor, a compound A undergoes a reaction. The chemical that is coming in is undergoing a reaction here. So it is transformed into chemical B. possibly a reaction A transforming B. The volumetric rate of consumption of A, how much amount of A is consumed to transform B, right? So volumetric rate means with respect to time. In other words, how much mole of A is consumed with respect to time per unit volume of the liquid stream. Alright, so that's called as volumetric rate of consumption. Mole per volume is concentration upon time. So it is, in other words, it is dC by dt, differential, that is a change in concentration with respect to time, that ends up with a terminology called as volumetric rate of consumption, and it is defined as RC. This is the rate equation. RC is equal to K1CA. So this is the rate of reaction. So let us look at that a little later. Develop unsteady state balance equation for total and component A. Total balance and component A. For total, all the chemical together and individual component A, we have to develop the balance equation. Let's look at the system what we have developed. This is the block diagram as I mentioned to you. The flow rate comes in, the density row includes all stream, all components in the stream. CA refers to the only chemical A that comes in. Similarly, it goes to the exit stream. So inside the tank you have the volume P of the liquid having a density C rho, and that particular chemical A has a concentration of Ca. Now the same thing I have defined it in here. So you can pause the video and you can just read it up, and whatever I explained, the same thing is rewritten. Let me go ahead with the particular concept called as rate of reaction. Order of the reaction or the rate of reaction, they are linked. The rate of reaction is given by an order of the reaction. Order means the order to the concentration is an equation, right? It's a rate equation. For a zero order reaction, it is C power 0, Ca power 0. So it ends up as R rate equals to K naught. Whereas for the first order it is Ca power 1, for the second order it is K2Cs square. Alright, so in our case here we are given with first order rate equation, so it's the equation which will be using it. If at all I give you another case that it follows a zero order, you may have to use this equation, R is equal to K. If it follows a second order equation, then you have to use this equation, R is equal to Kc square. Right, so let's go ahead with the balancing equation. Now here in this case we are considering a case of R is equal to K1Ca, that is the first order rate equation. Now let us do the balancing under unsteady state condition. Means when I say unsteady state condition, there exists accumulation. Accumulation is not zero, right? So let's do the overall balance. When I say overall balance, you will have to consider the entire chemical that comes in here into the container and entire chemical that goes out. The difference between the two should remain here. So when I say total balance, I mean I'm considering all the chemicals coming in, going out and remaining there. It includes the solvent, chemical A, as well as if there is any other chemical coming along with it. If I say component balance, then I have to mention which component I'm referring. So if I say component A balance, only the A I have to trace, how much amount of A comes in, quantity per unit time, and how much it goes out. The difference must have remained there. Possibly it could have undergone a reaction also, right? So when I'm considering the whole thing, keep it in mind, when I'm comparing the total balance, reaction is within, it's not exit, right? So reaction doesn't come into picture when you do a overall balance. The reason is, when I say overall, the reactant A is a part of that particular system, product B is also part of the stream. So reaction happens within the component and it gets equally distributed. Whereas when I say component A comes, once it is reacted, it is no more. Whereas when you say a total stream, total balance, it is still there, maybe in the form of B. The total mass remains the same, it doesn't change, even if it is converted to another form, this B, right? So in the case of total balance, you do not come across reaction. When you write a component balance, you will have to consider reaction. Keep that in mind while doing the balancing of the equations. So rate of mass in, I'll write it as mass flow rate I'm supposed to write, but I have the terminology volumetric flow rate. So volume to mass I can convert by multiplying with the density of that particular stream. So which is rho I, Fi into rho I. Similarly, for mass flow rate out, I need the mass flow rate out, but I have the data on volumetric rate. Volume multiplied by density gives me mass. right? So the rate, volumetric rate means volume per time. If I multiply it by the density, kg per meter cube, that is mass by volume. Volume gets cancelled, you get mass per time. The term is mass per time. This term is also mass per time. Incoming and outgoing, the difference between the two should be accumulated with respect to time in the system. This is the accumulation term which is remaining within the system. Again, unit balancing, overall it should have a unit of mass per time. So how do I define it? With respect to time I have to write, so that's d by dt first I'll write. Then inside the bracket I need to get a term for mass of the liquid in the container. That is this container, the liquid stream here, the mass inside that I have to write it. Whether it is increasing or decreasing, changing with respect to time, I should be able to find. How do I write the mass? I know the volume of it, that is V, which may be changing with respect to time also. Maybe we'll have to verify that. If I know volume, I have to calculate the mass. That I can do it by multiplying with the density. So rho into V. So I have considered V into rho or rho into V. That is volume of the liquid in the container multiplied with the density of the chemicals in the container. All stream together. So this is the overall balance. In a similar line, we can write the component balance for A. Chemical A. You need to specify which chemical you are doing the component balance. Now here we get the rate of reaction coming into picture. Very similar to this, but one extra rate of reaction comes into picture here. The rate of A in, how much A comes in along with the incoming stream, minus how much amount of A goes out with respect to outgoing stream, minus how much of A is not available or consumed in the reaction. Right? So once it is undergoing the reaction, it is no more. It is converted to B. A is no more. It is lost in the form of a reaction. So that is why a minus. If at all you are considering a chemical which is produced, think what will happen. So if at all you produce a chemical, then it is added to the system, so product will be plus. That means you will, if at all if you have a rate of production of A, then we'll have to add it as plus. But in this case A is undergoing a reaction, it's a reactant, so you will get minus only. So plus 0, in other words, production is 0 in this case, right? So the other than this, whatever it remains or extra what remains, it will remain within the container itself. That we call it as rate of accumulation of A. So imagine some chemical A coming in, maybe 100 moles coming in here. Just imagine for a fraction of a second what will happen this way. 100 moles or 100 molecules, let me take 100 molecules coming in. Of that, maybe about 25 molecules are going out, and another 50 molecules are undergoing a reaction to B. So out of 100, 25 going up, 50 undergoing the reaction, still 25 is remaining. What happens to that? It remains within the container itself. It is not going out. If it was going out, we could have called it as no accumulation, and we could have called it as steady state. Under unsteady state, some amount of chemical, the component, remains inside the container. So that is why we call it as unsteady state. So converting it into terminologies. Rate is nothing but, again, it's a mass rate we are talking about. So mass flow rate we need, but we know the concentration as well as volumetric flow rate for the in and output flow rate. So volumetric flow rate multiplied by concentration. Concentration is mass of A per volume. Here it is volumetric flow rate, means volume per time. So when you combine these two terms, what you get is mass of A coming in per unit time. Volume per time, mass per volume. So that volume gets cancelled, mass of A per time. Exactly similar, use the logic for rate of A out. So F here is the volumetric flow rate, Ca naught is the concentration of A going out. And the consumption, it depends on the volumetric rate. Remember the equation that we refine here, right? So RC is equal to K1A, K1Ca. So that equation is applicable for the first order case. So it is the rate of reaction we'll write, which is per unit volume. So that is why we'll multiply with the volume of the container, that is V. So rate of reaction multiplied by V. Think about this. If at all there is zero order reaction, what would have happened? If you have zero order reaction, then you would have written K, because the rate of reaction for zero order is R is equal to K. It's a constant, right? So similarly, second order, you will write KCS square. So depending upon the rate of reaction, this particular terminology will change either as K, KCA or KCS square, depending upon whether it is 0, first, second order. For time being, let me go ahead with the first order reaction. So that will be equal to d by dt. Similar to this, what I told you, d by dt, that is at the rate how much mass of A, only A, let me consider only A, how much mass of A is accumulated within the container. So that is volume into the concentration of A, because volume multiplied by concentration means mass of A per volume. So overall it gives you the mass of A that is accumulated with respect to time. So throughout, if you refer it, it is the mass of A per unit time individually. So these two are the basic unsteady state balance equations. Let us do some analysis and simplify these two equations. Let me consider that there is a uniform mixing. So I would have written it as for uniform mixing condition, assuming that there is a uniform mixing. In such situation, the density of stream or the concentration of stream inside the container will be same as its exit value. That means density will be in the tank will be equal to density of the exit stream. Concentration of A in the stream will be equal to concentration of A in the exit stream. So let's make use of this particular concept here. So the first case, it is rho, Fi rho I minus F naught rho naught. That's what we have, dd by dt of V rho naught and FICI. The same equation I just have rewritten over here. So let us see what modification we can make use of that. So if we take a constant volume system, let me take three different cases here. One is constant volume system, another constant density system, and volume and density are same throughout. Alright. So if the volume is constant, what will happen? In the differential term what we have for the accumulation, the volume comes out. So I can write the volume outside of it. So it becomes F, I'll take the other side, it will become F by V, right? It becomes F by V, and in fact I can write it as rho itself. Rho, if there is a constant mixing, I can simply write it as rho naught, which is the exit, or even I can write it as rho, which is the constant volume, sorry, the density in the container, right? Remember, the density in the inlet and exit will not be same. Density in the container and the exit, that will be same. Okay, that is rho naught throughout for the two cases. So simplifying it further, for the case of component A. Component A, CAI. So I have taken CA naught in both the cases here, as I told you in the previous uh, explanation, that exit and the container will have the same concentration, right? CA naught and CA naught. So I have taken it out. So once you have taken it out, you take it on the other side. So it ends up as F by V, right? So it becomes K1CA d by dt of CA naught. So you can write it as F by CA, F by V into CA. Here it is dCA by dt, and you can club this CA naught. You can club this to CA naught, and you can write it as, and you can take it on the other side also. Now this is a differential equation. We will not solve this. We will keep it as differential equation, because there will be a lot of variables which are unknown. We will have to solve that. So we are expected to develop only the equations in the differential form. We will not derive it, as the all terminologies are unknown to us the numerically. Once you are aware of the, or numericals are, numbers are available for each, then you can substitute and simplify. Then you have to do the integration. So when you develop an equation, we call it as a design equation, right? So those design equations could be in the form of a differential equation, as you see here, or you can substitute or simplify based on some assumptions and integrate them. They are called as integral equations. So they are integrated form of equation. Ultimately we require the integrated form of equation. Keep in mind, all the differential equation, whatever differential equation you end up, need not have a mathematical solution in the form of an algebraic equation, or in the form of an equation. All right. So in such cases we may use something called as numerical method, or even graphical solution. Usually we go for the numerical solution for a differential equation, ordinary differential equation, or for a partial differential equation. You would have learned all these concepts in the numerical methods. So those concepts can be used over here, where the solutions, okay, analytical solutions are not available. Analytical solution means write CA in a form of in terms of equation T, right? You have to integrate it, and then you have to write CA in the form of an equation, right? After integration, all differential forms need not have an analytical solution wherein you can integrate and get one output equation. It may not be possible for all the equations, right? So in such cases you will be using numerical methods. Okay, let me go ahead with another case called as constant density system. Previously I've seen the constant volume system. The volume remained constant, density not constant. Input and output density were different. Now I'm considering constant density system. When I say constant density, remember volume is not constant. Volume varies with respect to time. So since the density is same, input and output, rho I, rho naught, rho, all are same. So the rho, it comes out of the differential form and you can get cancelled, right? So that Fi minus Fi naught equal to dV by dt. Similarly for component balance also, we could write it, but here what happens is the volume, since it is not constant, as well as CA, both are not constant, so you will have to divide this particular differential form to this way, right? So you have d by dt of uv, for example d by dx of uv, if you have it, you write it as v du by dx plus u dv by dx, right? In a similar way you will have to write it and simplify the equation. So here it is just simplified in the form so that we develop an equation dca by dt on one side and all other terms on the other side. So when you develop the equation, ensure that make sure that your dca by dt terms are on one side. That's a better option, dca by dt or dv by dt. So these terms, the differential form on one side, all other terms on the other side. That way you can write, or alternatively you can write an equation equal to 0. That could be your end equation. This is a simplified form of this particular integral equation. So I'm not going to go in detail of that anyways. So it's a simple algebraic analysis that you need to work out. Now the constant density and constant volume system. Here what we do is we consider the density and volume both are constant, not one by one, it's both are constant. So in both the constants, when you have it, so that is rho naught, rho I is equal to rho, one thing. Then volume, right? The volume with respect to time does not change. Now if that is the case, if you look at this equation, so that rho gets cancelled out anyways, right? So the same equation you'll have, since the constant density system which is true, so you'll get the same equation. Further, the volume is constant with respect to time, right? Constant volume system means with respect to time it remains same, so dv by dt, differential with respect to constant, is 0. So Fi is equal to F naught. So in such cases Fi will be equal to F naught. In the previous case you have seen, for the constant density system, Fi minus Fi naught, F naught is equal to dV by dt. In this case you had the constant density system, right? So in addition to that you add one more term, that is constant volume system. In this case you will have a constant with respect to time which is 0. So Fi minus F naught will be equal to 0, or Fi will be equal to F naught, right? Now coming to the component balance, when you write the component balance, the equation number 2 what we had derived earlier, so the same equation you can write it, but with the terminology v and rho both are constant. Here rho doesn't come into picture, so you can take the v outside, so that v I have taken out on the other side of the equation, so that one side you have dc by d naught, dc by dt, and other terms on the other side. So instead of ca naught you could write only ca also. Keep a note of that, ca naught or ca, you can make use of any one notation, both are correct, but cai means it is the input concentration. So we have developed the model equation for unsteady state case, considering three different things. One, we have considered constant volume, we have considered constant density, we have considered constant density and constant volume case, and for all these cases we have considered first order rate equation. So this particular rate equation, you can see here K1 Ca0, only this particular term changes if we change the rate of the reaction, that is the order of the reaction. If it is zero order it would be just K first order K1 Ca, otherwise it will be K1 Ca square. Throughout you will get the same kind of equation, but please note you will get this particular equation only in the case of component balance, not in the total balance. Only for component balance you get rate equation. That's for this class. Thank you.